Hello and welcome. This will be a lecture on count data models. In this presentation, I will first talk about count data examples. Then I will talk about the count data dependent variable and its properties. Then we will move to talking about the Poisson model, the properties of the distribution, as well as the coefficients and the marginal effects. Then I will talk about the negative binomial model, which is less restrictive than the Poisson model. And we will also talk about tests for overdispersion and the incidence rate ratios. And then we will continue with a little bit more sophisticated models called hurdle or two-part models. And then we will also talk about zero-inflated models. So here are a few examples of count data. First of all comes from consumer demand. For example, the number of products that a consumer buys on Amazon. It's a discrete number. Then we could have recreational data, the number of trips taken per year, family economics, the number of children that a couple has, and health demand, the number of doctor visits. So notice one property of the dependent variable. That is counts, which is a non-negative integer. So y would be equal to 0, 1, 2, 3, 4, and so on. There are several things to point out here. These are indeed numbers, but the sample is concentrated on a few very small discrete values. Like, for example, you can say, well, how many grains of rice do you consume? That's also could theoretically be counted, but it's just so much that you may not want to use how many grains of rice, but instead how many pounds of rice or something like that, and move more toward continuous variable models rather than the discrete variable models. So make sure that when you have data that is count data, the numbers are relatively small. You know, most of the sample is, say, within 10, 20, 30 as far as numbers, and you have very few observations beyond that. If you have numbers in the thousands and so on, then perhaps this is not a very good model to look at. Another thing that I can mention here is that, for example, the number of children that a couple has, that is definitely a discrete variable. However, there may be situations in which that could be turned into a continuous variable, like, for example, how many children per couple are in each of the countries. And in this way, you know, you'll have like a country with 2.3 children per couple in a given country, you know, if these are averages. So in this case, also count data models would not be applicable. So you need to have very specific situations in which you have counts, they're discrete, and they're, you know, and they're very small in values. Then is when you can apply these models. And to do these models, we usually have independent variables, and these are the factors that would affect the average number of the dependent variable. That would be the goal of these models. So we would move to discuss the Poisson model now. And this model predicts the number of occurrences of an event. And the Poisson model states that the probability that a dependent variable y will be a certain number, small y, is the following. So you have here, you have the probability of your dependent variable y being of a certain value, like 0, 1, 2, 3, 4, and so on, is equal to e exponent to the power of minus mu, mu to the power of y, divided by y factorial. That's the form of the Poisson distribution. And when we use this model, we usually use mu as the intensity or the rate parameter, and mu equals exponent of xi prime beta is how we put the independent variables right here into the model. So they come into the mu and they show up several times, a couple times in the formula. That's the functional form. So once we estimate the model, the way to interpret the coefficients is that one unit increase in x will increase or decrease the average number of the dependent variable by the coefficient expressed as a percentage. And I will give you examples in the next video how to do that. We will now talk about a couple properties of the Poisson distribution. The first one is equidispersion property of the Poisson distribution, and that is the equality of the mean and the variance. If you look at the formula, then we have the expectation of y given x would be the same or equal to the variance of y given x, and then that would be mu. So this property tends to be very, very restrictive and often fails to hold in practice, in which case we have over-dispersion in the data, which means that this variance right here happens to be greater than the mean. And we would need to adopt a little more flexible forms to deal with this over-dispersion in the data, and that is called the negative binomial model. Another problem with the Poisson distribution is what we call the excess zeros problem of the Poisson distribution, and that is that we have usually many more zeros in the data than a Poisson model predicts. So if you're drawing randomly from the Poisson distribution, you can have a certain, you will have a certain percent frequency into zeros, ones, and 2 and 3 and 4 categories, and so on. But if you look at the data, it turns out that the percent frequencies of zeros is a lot higher in real life data than the parametric form of this distribution. So that's why sometimes it would be better to use zero-inflated Poisson or negative binomial models to correct for this kind of issue. So for the Poisson model, one thing that we can calculate is the marginal effects of the variable on the average number of events, and this is by taking the derivative of the expected value of y with respect to xj, and that would be the coefficient beta j times the exponent of x prime I beta. And the interpretation of those marginal effects would be that one unit increase in x would increase or decrease the average number of the dependent variable by the marginal effect. So now we will talk about the negative binomial model. That is used with count data instead of the Poisson model if there is over dispersion in the data. So unlike the Poisson model, the negative binomial model has less restrictive property that the variance is not equal to the mean. So in this case, we would assume that the variance right here is equal to mu, which was the case before in the Poisson model, but now we're going to add a term here, alpha mu squared, and this is where this model would be a little bit less restrictive. Another functional form that we could use here is that the variance is equal to mu plus alpha mu, but for some reason this form is less used. So when we estimate the negative binomial models, one of the results that's shown in the output is this over dispersion parameter as well, and now we can test for over dispersion by just looking at this parameter. So we could estimate this negative binomial models and then use the hypothesis H0 of alpha equals 0 versus HA of alpha does not equal 0. So we would have three cases. If alpha is equal to 0, then you can use the Poisson model. If alpha is greater than 0, you have the over dispersion, which frequently holds with real data. And then if alpha is less than 0, then you have under dispersion, which is very uncommon. So I would recommend, instead of estimating the probit model, you just go ahead and always estimate the negative binomial model. And if alpha is equal to 0 or not significantly different than 0, then you're justified in using the Poisson model, but the negative binomial model also will work. And if alpha happens to be greater than 0, you definitely have over dispersion in the data. So we're testing again for this formula that we have here for the variance. We're testing for this parameter here, alpha. And if that expression is close to 0, then we have variance equal to mu. We're back to the Poisson model. Next, we will talk about the incidence rate ratios. And these are very similar to the odds ratios that we talked about before in the probability and logit models. So for the Poisson and negative binomial models, we could report these in addition to reporting coefficients in marginal effects. And the incidence rate ratios report exponent of beta of the coefficients rather than beta themselves, the coefficients. And an interpretation would be that incidence rate ratio of 2 would mean that for each unit increase in x, the expected number of y will double. That's how they're interpreted. So now I will talk about hurdle or two-part models. And these are similar to the truncated models that could be used instead of like a Tobit model. Very, very similar idea. So these two-part models relax the assumption that the zeros, whether or not they're events, or whether or not we have the 0 or we are in the positive part of the distribution, and the positives, the 1, 2, 3, 4, and so on, they come from the same data generating process or different ones. So an example where this could be applied at is when you have different factors may affect whether or not you practice a particular sport and how many times you practice your sport in a month. So for example, if you play tennis, it depends on whether or not you like to be active, on whether or not you have injuries and so on, a lot of factors like that. But how many times you practice may be a function of, how close you are to the tennis court and things like that. So or how expensive are the entrance fees and things like that. So usually the first part may be something like if you're liking something or you have propensity or health issues, concerns. Or the second part is more related to the price and the conditions. So you may have different variables affecting the first step and the second step of this decision. The 0 versus the positive side is the first step, and then the second one is how much or how many of these you have, which is once you're in the positive part. So if the process generating the zeros, F1, and the process generating the positive responses, F2, is different, then the two-part hurdle model is defined by the following probabilities. G of y would be equal to F1 of 0 if y is equal to 0, or this other expression if y is greater than or equal to 1. Now notice one thing. If F1 and F2 are 0, what would happen here? The first thing would happen is these two expressions would be identical, so they will cancel out. And so here we would have F2 of y for y greater than equal to 1, and here you would have F1, which is the same as F2 if y equals to 0. So we're back to the Poisson model, or the, I shouldn't say Poisson, it could be Poisson or negative binomial, but we're back to the one-step model where we have the same data generating processes for the two steps. Now we have a different. Here we would have F1 of 0 is the data generating process for this one, and we would need to correct a little bit for the fact that if they're positive, so that again we have this is the probability of it being 0. So what's the probability of it not being 0? Well, that would be 1 minus this, 1 minus the probability of it being 0. And then you also have this correction factor here. in order to balance the probabilities. So this now would be the expression of the probability that we would have an outcome that is 1 or above 1. So in this case, when we estimate these models empirically, the model for the zero versus the positive counts, like this model here, oops, let's go back, like the model here would be estimated using a binary model with the specified distribution. But we can also estimate this using a probability or logit model. So we're just looking at whether or not we have a zero or positives, where the positives are coded as 1. And then we would have a truncated model here on the second one, where we're only considering the positive numbers and what affects those positive numbers. And finally, I will talk about zero-inflated models. And they're used with count data when there is excess zeros problem. So this model lets the zeros occur in two different ways. First, as a realization of the binary process where z equals 0, and as a realization of the count process when the binary variable is equal to 1. So let's consider this example. You either like hiking or you don't. If you like hiking, well, if you don't like hiking, then you're not going to be going on any hiking trips, I assume. But if you do like hiking, the number of hiking trips that you can take is 0, 1, 2, 3, and so on. So you may like hiking, but you may not take a trip this year. You might not have a vacation, or something else might come up, you might be busy, and so on. So in this case, you have the zeros generated from two processes. The first one is if you don't like hiking, you're not going to go hiking. But the second one is you may like hiking, but you may just happen that you don't go to take a trip this year. And because of this, we're able to generate more zeros in the data because it's coming from two different processes. So if the process generating the zeros F1 and the process generating the positive responses is F2, then we have the formula for the zero-inflated models for different probabilities. And look at this. If you have y equals 0, this is the probability of F1 would be equal to 0. So this is what we had before. We also had before that if F2 of y, that's the probability of y being 1, 2, 3, and 4, and for cases that y is greater than 1 and so on. And you again, like the case before, you multiply by 1 minus f1 of 0. Why? Because this is the probability of y equals 0, so if it's not equal to 0, that would be 1 minus f1 of 0. So you need this correction term here. But another thing that you're also augmenting is this expression right here, because the zeros may come from F2, from a zero response to the second data generating process. And then again you correct this by the probability that this is not coming from the first process. So you have just a little bit more zeros in the first step is all we're trying to do here. So the zero-inflated models generally less used than the Herder model, but it can handle these excess zeros problem. And another thing that is very interesting about this model is that you again could have different variables affecting the first step and the second step of this process. So you may have factors that affect whether or not you like hiking, but different factors of the number of hiking trips that you're taking. So this was a brief overview on count data models. So next, please go ahead and watch the count data models example, as well as the different programs that I have estimating those models. Thanks for watching.